Bernoulli's equation. Bernoulli's equation is nothing but when you're going to apply law of conservation of energy to the flow of the fluid, then we get the Bernoulli's equation. So before starting Bernoulli's equation, we will define what is fluid, what is flow of fluid, and which are the different flow of fluids which are available. So what is fluid? Fluid is a substance that continuously deforms under an applied shear stress. That means if you apply a shear stress to any substance, there is continuous deformation or continuous movement of the different layers of the particles, then we will call it as a fluid. Okay, and fluids are a subset of phases of matter and include liquid and gases. Now what is shear stress and what is shear force? So shear stress is a force that is acting on a parallel to the surface and cause one object to slide over each other or slide over another, and because of that there is a continuous deformation which exactly happen in the case of the fluid. Shear force is nothing but force that pushing one part of the body in one direction and another part of the body in the another direction, opposite direction. Same as we have a elasticity, so there we have a shear force. So that is basically shear stress and shear force. Okay, so what is flow of fluid? So fluid flow is defined as a flow of a substance that do not permanently resist the alteration in the shape. That is called as a flow of fluid. Fluid flow can be divided into fluid statics and fluid dynamics. Now coming to the types of fluid flow. Now fluid flow, its first class or type is steady and unsteady flow. So steady flow is one in which fluid parameters or characteristic like velocity, pressure, density do not change at particular point, while in the case of unsteady flow, these parameters are going to change with respect to time. Coming to the next part, uniform and non-uniform flow. So uniform flow is a flow in which velocity at given time does not change with respect to space, while in the case of non-uniform flow, this velocity at particular time is going to change with respect to space. Okay, coming to the laminar on and turbulent flow, which we always here in the pharmaceuticals. So laminar flow is a flow where the fluid particles move along a well-defined path, or we will call it as a streamline flow. Coming to the turbulent flow, the path or the movement of the particles, fluid particles, is going to be very irregular. Sometimes we also have a zigzag pattern of the flow, right? So that is exactly the turbulent flow. Compressible and incompressible, where incompressible with respect to time there is no change in density, while in the case there is change in density, while in the case of incompressible flow with respect to time there is change in the density of the fluid, then we will call it there is no change in the density, then we will call it as incompressible. So in the compressible, with respect to time, change in the density, while in the case of incompressible there is no change in the density. Coming to the next class, rotational and irrotational flow. So when while having a flow, if fluid particle are going to have angular velocity or they are going to rotate around their own axis, then we will call it as a rotational flow. And when they don't have any angular velocity or they are not going to rotate around their own axis, then we will call it as a irrotational flow. Okay, now moving ahead, as we are going to look into the Bernoulli's equation, and it is also related to the law of continuity. First we will look into law of continuity. So law of continuity said the rate at which mass enters the system is exactly equal to the rate at which mass leaves the system. So flow rate, it's going to tell you regarding the flow rate. So flow rate is equal product of area into velocity. Now here we have got A1 V1. A1 V1 represent the flow rate at inlet, and this A2 V2 represent the flow rate at outlet. So this is law of continuity. Now moving ahead, when, as we have said in the earlier also, when the principle of law of conservation of energy is applied to the flow of fluid, the resulting equation is called as a Bernoulli's equation or the Bernoulli's theorem. So Bernoulli's theorem says in a steady state the total energy per unit mass consists of pressure energy, kinetic energy, potential energy, and the total energy is going to remain constant. That means total energy at inlet is exactly equal to the total energy at outlet. Now Bernoulli theorem or equation, it is applicable to ideal fluid. So whenever we will talk about Bernoulli's theorem, the fluid in a consideration or fluid in a picture is going to be your ideal fluid. What is ideal fluid then? A fluid with the irrotational flow. That means the fluid particles are not going to have any, they are not going to rotate around their own axis. There is no change in density. It is incompressible and they are going to travel in one path, right? So it is going to have a streamline flow or it is going to have a laminar flow. Okay, so that is basically a ideal fluid which we are going to consider while explaining the Bernoulli's theorem. Now this consider this as a pipeline through which your fluid is going to travel or it is going to flow, right? So A is my inlet and B is my outlet. So according to the statement of the Bernoulli's theorem, the total energy at A is exactly equal to the total energy at outlet. Okay, so I am going to give some energy, shear stress to my substance so that it can have a flow, right? So fluid will have a flow because of the energy that is being provided by the pump. Okay, so the total energy at A and total energy at B is nothing but it is potential energy plus pressure energy plus kinetic energy, right? So A, the same thing has been written over here. B, it is the energy at B is nothing but potential energy at B, pressure energy at B plus kinetic energy at B, right? Uh, Same thing is written over here. Now talking about potential energy. Now what is potential energy? Potential energy is nothing but the energy that is being possessed by any fluid, any substance, that is because of its position or its height, right? So that is exactly the potential energy, and potential energy is a product of mass, height and acceleration due to gravity. Now we will convert this the mass and gravity in terms of weight. We know that weight of a body is equal to mass into the acceleration due to gravity. So I'm going to consider the fluid that I have considered, it has got a unit weight. Okay, so that means I'm going to consider W is equal to 1. Okay, so in my potential energy, if I replace this W by 1, then I'm going to get potential energy is equal to X. Now what is X? X is nothing but the height that we have considered. In this case, um, here we have said ki our inlet it as height XA from the floor and our outlet is at height XB from the floor, right? So the same way, so finally when we write the potential energy at A, it is nothing but XA because we have considered it for a unit mass of a liquid or fluid, and potential energy at B is nothing but XB, that is nothing but height of the outlet from the floor. Okay, so if I rewrite that term again, I will get total energy at inlet is equal to XA, which is nothing but the potential energy plus pressure energy at A plus kinetic energy. Same way we have written it for the outlet. Now moving ahead, we will talk about what is pressure energy. Now pressure energy, it is the energy of a fluid when flowing under a pressure. So with the help of pump, we have given some external pressure or external energy. So we also have a pressure energy, right? So we know that pressure is this force per unit area. So if we rewrite the term, force exerted will be a product of pressure into A, right? So what is pressure energy? Pressure energy is nothing but it is going to be capable of exerting force of P into A that is moving through a distance L. Okay, so I will write pressure energy as, or I will present pressure energy as a product of pressure into area into the length. Now, as I know, area and length is equal to the volume. So I will write pressure energy as a product of pressure into the volume, right? Further, I know that density is equal to mass upon volume. Volume is mass upon density. So if I rewrite the term, finally I will get the equation that pressure energy is equal to pressure into weight of the fluid divided by acceleration due to gravity into density, right? Now, again, I'm going to consider, because for the potential energy, I have considered fluid with a unit mass. So here also I'm going to consider it for the unit mass of the fluid. So I will replace the W, which is weight of the fluid, by 1, and I will get pressure energy as pressure that at particular point divided by acceleration due to gravity into the density of that particular liquid, because the density is going to remain same because it is an incompressible fluid. So at point A and at point B, this density is going to remain the same. So again, I have rewritten the total energy at A and total energy at B. So total energy at A is going to be XA, which we have already proved, plus potential energy. Now we have written potential energy as pressure at A divided by acceleration due to gravity into density of a fluid, plus kinetic energy at A. Similar way, B at P, or at outlet, we have total energy is equal to the potential energy, which is nothing but the height of point B from the floor. So XB I'm going to write, plus pressure at B divided by acceleration due to gravity into density plus kinetic energy at point B. Okay. Now talking about the kinetic energy. Now kinetic energy, as we know, kinetic energy is half mv square, right? Where we have v is nothing but the velocity of a body, or we will say velocity of a fluid, and m is nothing but the mass. So again, I'm going to rewrite the mass by considering weight in a picture. So I will get kinetic energy is equal to half w v square divided by g. Again, I'm going to consider this for a unit weight of fluid, or unit weight of fluid. So I'm going to write kinetic energy is equal to v square divided by 2 into acceleration due to gravity, right? So this way, again, I'm going to rewrite the total energy. Again, I'm going to rewrite the total energy at point A. It is going to be XA plus pressure at A divided by acceleration due to gravity into density, plus velocity at point A square divided by 2 into acceleration into gravity. So same way, I have rewritten the total energy at point B, and according to the statement of the Bernoulli's equation, this everything, total energy at point A is exactly equal to the total energy at point B, and it is going to remain constant, right? So this is exactly the Bernoulli's equation. Now, it is said that during the transport of some energy, or when your fluid is going to travel through the pipeline, some energy is converted into the heat due to, and some there is frictional loss of energy. So I am going to minus that energy loss from my inlet. At the same time, at inlet, we have provided some energy or work done to the fluid. So I'm going to have plus W work done at inlet. Okay, so this is called as a Bernoulli's theorem or Bernoulli's equation. Now, what is the application of the Bernoulli's theorem? Bernoulli's theorem is used in the measurement of rate of fluid flow using flow meters, and it is also applied in the working of centrifugal pumps. In this, kinetic energy is converted into the pressure energy. Now, some energy losses that has been considered in the case of Bernoulli's equation. So that's why we have that minus F, right? So it can be frictional losses, it can be losses due to the fitting of the pipeline, it can be due to the enlargement or it can be the contraction of the pipeline. So this is all about the Bernoulli's equation. Thank you so much.